Welcome to the deep dive. Today, we're kicking off something a bit special. It's the first part of our new series, focused entirely on prepping you for the CSWIP 3.1 Welding Inspector Exam.
That's right.
Our mission here is pretty simple. Take those tricky multi-choice questions you'll face, unpack them, and really get to the core of the concepts.
Yeah, it's not just about getting the answer right. It's about the why.
Exactly. We want to make sure you walk away with clear, practical knowledge that sticks. Useful for the exam and useful out there in the field.
Absolutely.
Okay, let's jump straight into our first question then. Right, question 1, it asks, which of the following elements, which may be added to steel, has the greatest effect on creep strength? And the options are A, tungsten, B, manganese, C, carbon, and D, molybdenum. Okay, so creep strength. It sounds technical, maybe a bit mysterious. For someone hearing this, what exactly is creep and why should we care about it, especially in places like, say, power plants?
Right. It does sound a bit sci-fi, doesn't it? But creep is very, very real. Imagine you've got a component, maybe a pipe, under stress, but it's also really hot, like really high temperatures for a long, long time, think years, even decades.
Okay.
Even if the stress isn't enough to break it right away, over that time, at that high temperature, the material can slowly stretch, permanently deform.
Okay. Like it's slowly yielding.
Exactly. It creeps. So creep strength is just the material's ability to resist that slow, high-temperature stretching under sustained load. And in a power plant or chemical processing where things run hot for ages, well, you can see why it's critical. You don't want parts slowly deforming until they fail.
No, definitely not. That sounds like a recipe for disaster. So it's about long-term endurance under heat and stress.
Precisely. It's the long game.
Okay, so looking at our options,
Well,
tungsten, manganese, carbon, molybdenum, which one's the star player for boosting this creep strength?
Well, the standout here, the one with the greatest effect among these choices, is D, molybdenum.
Molybdenum. Okay, why? What does it do?
It's actually quite fascinating. Molybdenum has this ability to form very stable carbide particles within the steel, especially at high temperatures. Think of these carbides like tiny little anchors spread throughout the steel structure. Yeah, they effectively pin the grain boundaries and make it harder for the internal structure, the dislocations, to move around. And it's that movement that leads to creep.
I see. So it locks the structure in place even when it's hot.
You got it. It provides that high-temperature structural stability. Tungsten can help too, but molybdenum is particularly effective for creep resistance in many common steels. Manganese and carbon are essential for other steel properties, of course, but they don't have that same specific impact on resisting long-term creep like molybdenum does.
Right.
So for you listening, understanding this link between molybdenum and creep resistance is vital if you're inspecting or specifying materials for high-temp service. It's about safety and lifespan.
That makes perfect sense. Engineering the material for the job. Okay, let's switch gears to another really fundamental topic, preheat. Question 2 asks, which of the following are considerations for the selection of a preheat temperature? Options are A, carbon equivalent, joint design, welding process, and plate material quality. B, all joints over 25 millimeter thick, hydrogen levels, welding process, carbon equivalent. C, arc energy, material thickness, hydrogen scale, and carbon equivalent. Or D, all of the above are considerations. Now, preheating, it's obviously important, but this list of factors suggests there's quite a bit to think about. What are we actually trying to achieve when we preheat a joint?
Yeah, preheat isn't just about warming things up randomly. It's very strategic. There are a few key goals. Primarily, you want to slow down the cooling rate of the weld area.
Slow cooling, why?
Well, slower cooling gives the metal structure more time to transform nicely, making it less brittle. It also crucially allows any dissolved hydrogen from the welding process to diffuse out.
Hydrogen. That's the big one for cracking, right?
Yeah, exactly. Hydrogen-induced cracking, or HICC, is a major headache. Preheat helps hydrogen escape before it can cause trouble. And thirdly, it reduces the temperature difference between the hot weld and the cooler base metal, which minimizes residual stresses and distortion. Less stress, less warping.
Okay, slow cooling, hydrogen removal, stress reduction. Got it. So looking back at the options, which set of factors best covers those goals?
Right. Option C. Arc energy, material thickness, hydrogen scale, and carbon equivalent is the most comprehensive and accurate list here.
Let's break that down. Arc energy.
That's your heat input, essentially. It directly affects how quickly things cool. Higher arc energy might mean less preheat needed sometimes, but it's a balance.
Okay, material thickness. That seems obvious.
Yeah, thicker materials just soak up heat much faster. They act like huge heat sinks, so they almost always need more preheat to keep that cooling rate slow enough.
Makes sense. Hydrogen scale.
That relates directly to the risk of hydrogen cracking. If you've got a process known to introduce more hydrogen or a material susceptible to it, you'll need a higher preheat. It's about managing that risk.
And finally, carbon equivalent, CE.
CE is a calculated value that basically tells you how hardenable the steel is, and therefore how susceptible it is to cracking. Higher CE usually means you need a higher preheat temperature. Simple as that.
So why not D? All of the above. Options A and B have some right terms, too.
They do, but option C lists the most critical and universally accepted factors. Joint design in A matters, but it's often implicitly covered by thickness and restraint. Plate material quality is a bit vague. Option B mentions a specific thickness, which isn't a universal rule for selection, and hydrogen levels is better captured by hydrogen scale, which considers the source and risk. So C is the proudest, most accurate list.
I see. It's about the precision of the factors listed.
Precisely. And these factors, they aren't just theory. They're what you use every day when reviewing a welding procedure specification, a WPS, or checking quality control on site. Getting preheat right prevents failures.
Okay, that's really clear. It emphasizes how practical this knowledge needs to be. Let's move on to something visual now, inspecting fillet welds. Question 3. During visual inspection of a fillet weld with even leg lengths of 15 millimeter, the throat thickness is measured at 8.5 millimeter. What is the fillet weld's profile? Options: A, convex, B, miter, C, concave, D. Both A and B are correct. So we've got numbers: 15 millimeter legs, 8.5 millimeter throat. How do we turn that into a description of the weld's shape? What's the inspector seeing?
Right, this is bread and butter visual inspection stuff, taking a measurement and understanding what it means for the weld geometry. The key here is the relationship between the leg length and what we call the theoretical throat thickness for a perfectly shaped fillet weld, which is known as a miter fillet.
The miter fillet, like a 45-degree angle face.
Exactly, perfectly flat face, equal legs. For that ideal miter shape, the throat thickness is calculated as roughly 0.707 times the leg length.
Okay, 0.707 times the leg length.
So in this case, with 15 millimeter leg lengths, the theoretical throat for a perfect miter weld would be 0.707 times 15, which comes out to about 10.6 millimeters.
10.6 millimeters, but the measured throat was only 8.5 millimeters.
Exactly. Our measured throat, 8.5 millimeters, is less than the theoretical miter throat of 10.6 millimeter. When the actual throat is less than the ideal theoretical throat, it means the weld face is sort of sunken in or dished, and that profile is called concave.
Concave, like a cave, sunken in.
Precisely. So the correct answer is C, concave.
Okay, so what would convex or miter look like in terms of measurement?
Good question. A miter weld would have a measured throat pretty close to that calculated 10.6 millimeter. A convex weld bulges outwards. It has excess weld metal, so its measured throat would be greater than the theoretical 10.6 millimeter.
Right, more than 10.6 millimeter.
Yeah. So miter is ideal, around 0.707x leg. Concave is less, convex is more.
And this matters because it's not just about looks, is it?
Definitely not just looks. The throat thickness is the critical dimension for the strength of a fillet weld. A concave profile means you have less load-bearing material than intended for that leg size, which directly impacts its strength. Stress concentrates differently too, so identifying the profile is crucial for judging if the weld meets requirements.
Excellent breakdown. Okay, let's get into the welding process itself now, specifically manual metal arc or MMA. Question 4. For a given voltage and current settings on a MMA welding plant, when the arc length is shortened, which of the following will be most affected? Options: A, the current will increase, B, the current will decrease, C, the voltage will decrease, D, the voltage will increase. This sounds like it's about how the power source behaves. What's the relationship between arc length, voltage, and current in MMA?
Yeah, this gets right to the heart of how typical MMA power sources work. Most machines used for MMA are what we call constant current, or CC power sources.
Constant current, meaning the amps stay steady?
Pretty much, yeah. The machine tries its best to keep the current output stable at whatever the welder sets it to, even if the distance between the electrode tip and the workpiece, the arc length, changes slightly.
Okay, the machine compensates.
Right. Now, think about the arc itself. It's basically a gap of plasma that electricity has to jump across, like a resistor. If you shorten that gap, shorten the arc length, you're making the path for the electricity shorter. What does that do to resistance?
Shorter path, less resistance.
Exactly, less resistance. Now, remember Ohm's law, VIR. Voltage equals current times resistance. If the machine is keeping the current I constant and the resistance just went down because the arc got shorter, what has to happen to the voltage V?
If I is constant and R goes down, V must go down too.
Bingo. To maintain that constant current flow across a lower resistance, the power source automatically decreases the voltage across the arc.
So the answer is C. The voltage will decrease.
That's the one. The current stays relatively constant because it's a CC machine, and the voltage drops because the arc resistance dropped.
It's not intuitive, maybe, but it makes sense when you think about the power source's job.
Absolutely. And understanding this helps welders control their puddle by adjusting arc length, and it helps inspectors understand potential causes for arc instability or voltage fluctuation they might observe.
Great explanation. Okay, one final question, sticking with MMA. This deals with a common frustration, arc blow. Question 5. MMA welding process. Which statement is true about reducing arc blow? Change from AC to DC current, B. Change from DC to AC current. Change from DC negative to DC positive. Arc blow. I've heard welders complain about this. The arc just wanders off. What's causing that magnetic mischief?
Oh yeah, arc blow can be incredibly frustrating. It's exactly like you said, the arc gets deflected from where you want it to go. It gets pushed or pulled, usually towards the ends of a plate or into corners. It leads to spatter, undercut, poor fusion. Basically a poor quality weld and a headache for the welder.
So what's pushing it? Magnets.
Essentially, yes. It's caused by magnetic fields interacting with the arc. This is primarily a problem when you're welding with direct current, DC.
Why DC specifically?
Because DC flows in one constant direction. This creates a steady magnetic field around the electrode, the workpiece, the cables. If that magnetic field isn't perfectly symmetrical around the arc, maybe because you're near an edge or a ground clamp or existing magnetism in the steel, the imbalance creates a force that pushes the arc.
Like unseen magnetic winds blowing the arc off course.
That's a good way to think about it. Now, considering the options, how can we combat these steady magnetic winds?
Well, option B suggests switching from DC to AC. Does that help?
That's the most effective solution listed here. So the answer is B. Arc blow can be reduced or eliminated by a change from DC to AC current.
Why does AC work better?
Because alternating current, AC, is constantly reversing its direction, right? 50 or 60 times a second, typically. That means the magnetic field it creates is also constantly flipping back and forth. Those rapidly changing magnetic forces effectively cancel each other out over time. The arc doesn't get a consistent push in one direction, so it stays much more stable.
The constant switching disrupts the steady magnetic force.
Precisely. Changing DC polarity, option C and D, might sometimes slightly alter the magnetic field and offer minor relief in very specific cases, but it doesn't solve the fundamental problem of a steady directional magnetic field like switching to AC does. And switching to DC from AC, option A, would likely make arc blow worse if magnetic issues were present.
Got it. So AC is the go-to fix if arc blow is a major issue with DC.
Generally, yes. It's a key piece of practical knowledge for troubleshooting on the job, both for the welder trying to maintain control and the inspector diagnosing weld defect causes.
Fantastic. Wow, we've really covered some crucial ground today for anyone prepping for that CSWIP exam or just wanting to deepen their welding knowledge. We looked at creep strength, digging into why molybdenum is so important there.
Yep, those stable carbides.
Then the critical factors for preheat arc energy, thickness, hydrogen, CE, all about avoiding cracks and stress.
Slow cooling is key.
We learned how to translate fillet weld measurements into profiles, concave, miter, convex, and why that matters for strength.
That .707 calculation is handy.
And we dove into MMA power sources, understanding the constant current principle, how arc length affects voltage.
Voltage drops when the arc shortens.
And finally, tackling arc blow by understanding why switching from DC to AC is often the best fix.
Fighting those magnetic fields.
It really shows how all these pieces fit together to ensure you get a sound, reliable weld in the end.
It absolutely does. And hopefully this dive highlights that it's not just about memorizing answers. It's the understanding behind the answers that truly matters. Knowing the why gives you the ability to problem solve, to adapt, to make informed decisions out in the field. That's far more valuable.
Couldn't agree more.
So maybe a final thought for everyone listening. As you study these concepts, keep asking yourself, how does this apply practically? How will understanding this make me a better inspector, a better welding professional?
That's a perfect challenge to end on. Think beyond the exam to the application. Thank you so much for sharing your expertise today, and thanks to all of you for joining us on this deep dive. Keep exploring, keep asking questions, and we'll catch you on the next part of our CSWIP prep series.